We're going to continue our discussion on logarithmic differentiation today in this section. And what we're going to work with is finding the derivative of something that looks fairly complex. And when I say complex, it's going to have multiple power rules, or multiple product rules, multiple quotient rules, or a combination of all of those different rules. And through logarithmic differentiation, we can actually make the process a little easier, and we can remove the product and the quotient rule needs. So the first thing you got to remember is the expansion rules for natural logs and logs in general. So one thing I do like to talk about, we can do log or natural log. Remember, they are talking about the same thing, except for natural log is base e, where log is the common log is base 10. So if we're multiplying two quantities, and we're taking the log of those two quantities being multiplied, we could break this up into the log of a plus the log of b. Likewise, if I had the log of a over b, then I can take this as the log of a minus the log of b. And if I had log of a to the b, I could bring that exponent to the front of my log, so I have b log of a. Three very important rules as we get into being able to expand things and take the differentiation through logarithms. So in this example that I have here, we're going to find f prime of x, given f of x equals x radical x squared minus 1. Out here they're going to give us some restrictions on x. X has to be greater than 0, and that'll play in, you'll see that here in a second, why that's important that we put that in there. So the first thing I'm going to do is change this f of x to a y. So I'm going to have y equals x, and I'm going to change my radical x squared minus 1 to x squared minus 1 quantity to the half. So I have a nice fractional exponent. If I do one thing to one side of an equation, I got to do it to the other, and that's been ever since Algebra 1. So I can take the natural log of both sides of this equation, and I'm not going to change anything about the equation. I'm just changing the look of it. Now, on the right side here, I can go ahead and expand this out using my rules of expansion for logs. So I have the natural log of y is going to equal the natural log of x plus 1/2 the natural log of x squared minus 1. I did a couple of things there. I have multiplication. So multiplication can break up through addition of natural logs. And I have a power that's going to come to the front of my natural log. You have to be very careful as you do this, because we cannot bring this 1/2 to the front of everything, because that 1/2 power is just to, or just with, that x squared minus 1. So be careful with that as well. Now I can go ahead and find the derivative of this implicitly. So the natural log of y, I know the derivative of that is 1 over y. I took the derivative of y, so it's dy dx. Derivative of natural log of x is 1 over x. And derivative of 1/2 natural log of x squared minus 1. I have my constant of 1/2. Derivative of natural log of x squared is going to be 2x over the original function x squared minus 1. Oh, I didn't talk about that x is greater than 0. So notice here we took the natural log of x. We know that we can't take the natural log of an x value that is less than or equal to 0. So that's why we have to put that restriction on there that x has to be greater than 0. And that's the only reason that's going to be out there for us. For the most part, you can kind of eliminate that and put that onto the side burner there. Now what we're going to do is get dy dx by itself. In order to do that, we're going to multiply both sides by that y. So I get dy dx is going to equal, I'm going to put this nice bracket, 1 over x plus, here we can clean this up, our 2's cancel each other out, so we have x over x squared minus 1 times our y. But we know that y is the original function. So dy dx is going to equal, and I'm going to go ahead and actually do a couple of things in this step, since I'm running out of some room. I'm going to go ahead and find a common denominator as well here. So my common denominator is x times x squared minus 1. So I get x squared minus 1 plus x squared. And that's going to be multiplied by my y value, or x square roots of x squared minus 1. I can now go ahead and simplify. I have x squared plus x squared gives me 2x squared minus 1. My x's are going to cancel each other out here, and I have x squared minus 1 in the denominator and a radical x squared minus 1 in the numerator. Remember that x squared minus 1 radical is actually to the half power, so I can go ahead and cancel out one of those x squared minus 1 to the halves. So I'm going to end up with an x squared minus 1 to the 1/2 in our denominator. And that's going to be our derivative. Isn't that fun? Oh, as I ran out of room there. So there we go, 2x squared minus 1 over x squared minus 1 to the 1/2. Just got a new document camera, so I'm playing with it and learning as I go. Alright, here's our next example. We're given f of x equals x squared radical 3x minus 2 over x minus 1 squared, and x is going to be greater than 2/3. Again, not a major thing there, but something that we do need to think about. So as I look at this, we could do a product rule in the numerator, and we have a quotient rule. So who wants to do a big quotient rule with a power rule or a product rule inside it? Not going to be something that we're going to enjoy doing. But if we do logarithmic differentiation with this, so if I go ahead and take the natural log of both sides, and some of you can probably go ahead and split this up as well as you're doing it. I'm going to go ahead and write it out just a little bit. So we have the natural log of x squared radical 3x minus 2 over x minus 1 squared. I'm going to go ahead and expand this right side out. So I have the natural log of x squared, which is going to be 2 natural logs of x. I have a multiplication, or if it's a numerator, it's going to be addition. That radical becomes a half, natural log of 3x minus 2. In our denominator, we're going to show that by a subtraction. We're dividing, so we're going to subtract 2 natural logs of x minus 1. Now we can go ahead and find our derivative. Derivative of natural log of y is going to be 1 over y, dy dx. Derivative of 2 natural logs of x is 2 over x. 1/2 natural logs of 3x minus 2. Take the derivative of the function, which is going to be 3. We have our 2 already in our denominator, and then divide it by the quantity. Minus, again, here we have 2 over, the derivative of x minus 1 was 1, so we had 2 times 1, or 2, in the numerator, over x minus 1. Now we can go ahead and multiply the y over. We can also find a common denominator if you wish. Won't that be fun? I can already hear the groans. So our our common denominator, basically we have all these different denominators squished together. So we have x, or 2x, we have 3x minus 2, and we have x minus 1. So the 2 is going to get a 2 and a 3x minus 2 and an x minus 1. The 3 is going to get an x and an x minus 1. And the negative 2 is going to get an x and a 2 and a 3x minus 2. Good gracious. And that's all times that y value. So maybe we'll just leave that over here for just a second so we can go ahead and clean this up, this numerator up. So what we got? We got 2. I'm going to go multiply that out, I guess. So we have 4. We have 3x squared. We have a negative 3x and a negative 2x gives us a negative 5x plus 2. To that we're going to add 3x to x minus 1 times x minus 1. So 3x squared minus 3x. We have a negative 4x here multiplied to the 3x gives us negative 12x squared plus 8x. I'm going to go ahead and distribute that 4, clean this whole numerator up here real quick. We have 12x squared minus 20x plus 8. So our 12x squares, those cancel. That's nice, isn't it? We have 3x squared then. We have a negative 20x, negative 23x. And then we're going to end up with a negative 15x. So that's going to be gone there. And it looks like we have a plus 8 left over. And that's going to be over that denominator of 2x and 3x minus 2 and an x minus 1. And we're going to multiply that by our y value, which is x squared, square roots of 3x minus 2 over x minus 1 squared. And that's our dy dx. So what can we do to clean this up a little bit? Well, we have x minus 1 in our denominator, so I can go ahead and rewrite that first portion of our numerator. So we have our 2, that's going to stay here. Our x and our x squared, we're going to have an x on the top. Those are going to cancel. An x is going to cancel out. We have an x minus 1 to the third on the bottom. And we have 3x minus 2, a full one on the bottom and a half on the top. So we're going to be left with a 3x minus 2 to the 1/2 on the bottom. And that's going to be our nice dy dx. Isn't that fun? Alright. I have one more, believe it or not. Again, it's going to work very similar, so if you want to go ahead and try one on your own, go for it. If you don't necessarily like that, you can stay here with me and we'll try to get this one fairly quickly. So I'm going to go ahead and take the natural log of both sides, and I'm going to go ahead and break that up as well. So I have the natural log of x plus 1 plus the natural log of x minus 1 minus, since they're in the denominator, the natural log of x plus 2 and minus the natural log of x minus 2. So again, in the numerator it's going to be addition, it's going to be a positive natural log. Denominator is going to be a negative natural log. Hopefully your pre-calculus teacher taught you pretty well with logs and the property of logs. Go ahead and find our derivative. We have 1 over y dy dx. Derivative of x plus 1 is 1 over the original function of x plus 1. Derivative of natural log of x minus 1 is 1 over x minus 1. Derivative of natural log of x plus 2 is 1 over x plus 2. Natural log of x minus 2, derivative is 1 over x minus 2. So that's our derivative there. Interesting how it's kind of stair-step down, isn't it? Just all that. Something I see. Alright, go ahead and find a common denominator. Oh, good gracious, good grief. Looks like x plus 1, x minus 1. Oh, that's interesting. We should have multiplied those together. Wouldn't that have been a lot easier? Maybe somebody saw that and they said, hey, why don't you multiply this together? Could have done x squared minus 1 over x squared minus 4, couldn't we? Done a chain rule and been done. Oh, well. That's the way life goes. Let's see. So that's our denominator. We're going to have our 1. It's going to get an x minus 1, x plus 2, and x minus 2. So really x minus 1 and x squared minus 4. This one here is going to get an x plus 1. It's going to multiply to x squared minus 4. We're going to subtract. The x plus 2 is going to get an x minus 2 and an x squared minus 1. And the last one's going to get an x plus 2 and an x squared minus 1. So I'm going to guess a lot of this is going to cancel out for us. So let's see what happens. Let's see. We got an x to the third minus x squared minus 4x plus 4 from the first term there. Multiplying this one out here, I get an x to the third minus plus x squared minus 4x minus 4. Multiply the negative and this together, so we get a negative x to the third plus 2x squared minus, actually a plus x and then a minus 2. And we're going to have this one over here, so minus an x to the third. We're running out of room. We have a plus 2x, so minus 2x squared. We have a negative 1x, but with a negative of that, so plus 1x. And then negative 2, the opposite of that, we're going to have a positive 2. Now, let's see what happens. We have x to the third plus x to the third is 2x to the thirds, but minus 2x to the third, so those are going to cancel. We had a 4 here and a negative 4 there, our 2 and our negative 2, those are going to cancel. I'm liking what I'm seeing. Our x squareds are going to cancel, and our 2x squareds are going to cancel. Isn't this great? What do I got left? I got a negative 4x, I got a positive x, and a positive x. Looks like I should have more x's there somewhere. Oh, there we go. Negative 4x and a negative 4x is negative 8x. And then plus 2x gives us a negative 6x. And that's going to be over that denominator, x plus 1, x minus 1, x plus 2, x minus 2. So I'm going to just go ahead and write it as x squared minus 1 and x squared minus 4. And that equals 1 over dy, 1 over y dy dx. I can go ahead and multiply my y over now. So I get a negative 6x over that x squared minus 1, x squared minus 4. So they're going to multiply by an x squared minus 1 over x squared minus 4. Go ahead and cancel those out. Those are going to be gone for me. And I'm going to get a negative 6x over x squared minus 4 squared. And that gives me my final answer. If you want to go check that with the quotient rule, by all means, check it with the quotient rule. And that gives you an idea of where we can make something that looks very ugly, very nasty, that has a lot of quotients and powers and product rules together. We can expand that out a little bit using our natural logs and our knowledge of logarithmic differentiation to make our life a little easier. Good luck and enjoy implicit logarithmic differentiation. Love that word.